Everybody see that okay? Okay. All right, so we're going to start our, basically in continuum mechanics, what we're trying to do is we're trying to understand the deformation of continuous bodies, right? And a continuous body could be, anything that's continuous, right? Anything solid. It could be this microphone, it could be the earth, right? Of course, the earth is not, 100% totally solid. There are cracks and other things in there, but, if you look at large enough scales, then you can assume that it behaves like a single body, right? Nothing is actually solid, right? Everything's made of atoms, which are discontinuous things, right? So we're going to be looking at, trying to describe, initially, later we'll definitely, when we talk about field equations, we're going to be talking about, basically conservation of energy, which is not a concept like deformation or motion, but we're going to start with focusing on conservation momentum. Conservation momentum is, when we say conservation momentum, it's really just a graduate school version of F equals ma. Who's ever heard of that? Like Newton's second law, right? F equals ma, right? So in F equals ma, we're talking about the motion of solid bodies, rigid bodies, right? So if I throw a ball through the air and we solve it using Newton's equations, we don't concern ourselves with the deformation of the ball itself, right? But in continuum mechanics, we would, right? So we're not just, yes, we're including the motion of the ball flying through the air, but we would also say, consider the motion of the deformation of the ball when it hits something, right? When it hits the ground, the ball is going to deform a little bit, and that's the kind of thing we're trying to describe, right? And so we're going to start, we're talking about motion, so we're going to start with something that we call kinematics, and kinematics is basically just the geometric description of motion. And the kinematics are going to lead us into strain, right? And strain is just a normalized deformation, right? Everybody remembers strain from your undergraduate mechanics class, right? And I'm going to have some notes to kind of review that here in a second, but basically, in the most elementary sense, strain is like the change in length over the original length of something, right? And so, the change in length, that has units, right? A change in length has units. It's like deformation, right? I pulled on the spring and it moved it 1 meter, right? That has units. But then we divide by a length, and so it makes it unitless, right? So we're normalizing the deformation by something, and that makes it unitless. And the reason that we want that is ultimately with strain and some constitutive model, we can develop the concept of stress. And what stress is like normalized force, right? If you remember the undergraduate mechanics notion of stress was like a force divided by an area, right? And the reason we want normalized quantities, or we prefer normalized quantities, is because it gives us a way to compare the strength of materials, right? So, for example, if we go to the lab, or if you go to the lab and you do a test on a material sample, you want your material sample. We often, if we're trying to basically detail properties of that sample, then we want to assume that the sample is homogeneous, right? So think about a piece of steel, right? If you look at a piece of steel under a microscope, it's of course not homogeneous. It has grain boundaries. If you look at it under, and further you go down, you get more and more details of inhomogeneity, right? But when you look at it with your naked eye, it looks homogeneous, right? It looks like one piece of material, right? And so, when we go to the lab, we can often get by with a fairly small sample, right? With a piece of steel, because the grains are much, much smaller, right? They're so small we can't see them with the naked eye. So they're much, much smaller than the size of our sample. And, size of a sample in, typical like material tests on a piece of steel, size of a sample would be like on the order of a few inches, right? However, then when you compare like a piece of concrete, think about a piece of concrete, right? A concrete is not nearly as homogeneous as steel, because even on the scale that we build things out of it, you can see the inhomogeneity. Think about a bridge, right? If you walk up next to a bridge and look at a column on the bridge, If you look at it with your eye and it's made of concrete, you can see aggregate, right? Rocks in there. So the inhomogeneity is, compared to the scale that we build things out of it, is much larger in concrete. So when we go to the lab to do an experiment on a piece of concrete, in order for us to, basically say that concrete is homogeneous, right? Because when we do an experiment, we're measuring global properties, right? I mean, does anybody remember from undergraduate geomechanics, or maybe your undergraduate solid mechanics class? Did you ever see a material test done to see how strong a material is? Basically, you put it in a mechanical loading apparatus and you press on it with a large press until something happens. It fails if it's concrete, or it deforms highly if it's steel or something like that, right? So, and the way we infer material properties from that material is from the global measurements, right? We measure the force on the load frame, right? We measure the displacement of the load frame, right? We're not measuring the displacement in 17 locations throughout the piece of material, right? We don't do that. We assume that we have this separation of length scales, that our sample is large enough that when we deform it, it's going to be homogeneous, right? So when you go to the lab to do an experiment on concrete, whereas with a piece of steel, you might have a sample that's on the order of a few inches. When you go to the lab on a piece of concrete, you need a much larger sample, right? Typically, a concrete sample would be maybe 4 inches in diameter and maybe this tall, right? Because it needs to be fairly large so that you can assume that the inhomogeneity. Think about if the piece of concrete was only 1 inch and you had a 1 inch piece of aggregate inside of it. Are you testing the concrete, the composite material, or are you just testing that one little rock that you're in there, right? So the point is to compare different materials, to compare steel to concrete, you can do two things. One, compare the strength of them. One, you can make the samples the same size and go in a laboratory and do experiments, right? Or you can have some way to normalize it, right? And that's what stress is, right? So, and that's how we can talk about the different strength of materials. So we have, you can go to the lab with a small piece of steel, and you can take the force and you divide it by the area, and now you know what the stress in the steel is. Same thing, you go with a piece of concrete that's much bigger. You can take the force divided by the cross-sectional area of the concrete, and then you can compare those two numbers at failure and say, okay, the steel is much stronger than the concrete, right? So we have to normalize by something in order to come up with a way to compare different materials and how they behave and deform. And what we'll see is that normalization is somewhat arbitrary. I know in undergraduate, stress is always just the force divided by the cross-sectional area, right? But what cross-sectional area? Right? You ever seen a highly deformed, like if you were to go and well lubricate the ends of a sample and compress it, that steel would grow in diameter, right? So what diameter? What cross-sectional area? The initial one or the final one? Right? Turns out it doesn't really matter as long as you're consistent. You can do it either way, and we're going to get to all that and talk about these different. So there's actually multiple notions of stress, and along with that, there's multiple notions of strain. So let's talk about those in a one-dimensional setting, just as a review. Right? So, let's imagine we have a bar, and it has initial length. Okay, and we're going to pull on that bar and deform it. So we'll pull on it on the end and deform it, and then it has the deformation here we'll call delta L, and then the total length. The total length then we'll call LF. Okay. So our typical notion of strain is actually what we should call the engineering strain. And that's delta L over L0, right? And if we write delta L in out, right, so it's the final length minus the initial length over the initial length. So often this ratio of the final length to the initial length is called the stretch. We often use the symbol lambda. And so we can rewrite this lambda minus 1. So that's the engineering strain. Am I writing large enough for you? Can you see that well? Okay. There's other names for this. Sometimes we call this the Lagrangian strain. You'll see that name again later, Lagrangian, because Lagrangian, later, either today or at the beginning of next class, we're going to talk about reference frames. And Lagrangian frame is always the original, sometimes called the undeformed frame, but basically it doesn't necessarily, I mean, the word undeformed is relative, right? Like if we're looking at this microphone, and you say, well, I'm not pushing on it, it's not deformed. But I mean, originally this steel was a piece of iron ore in the ground, right? So what's the undeformed configuration, right? So a better word is the reference configuration, like before we began to try to deform it, right? So, and of course, in a geomechanics setting, everything in the earth is deformed due to tectonic stresses. So it's like, we call the reference frame is a better word, or the Lagrangian frame. But sometimes again you'll hear the word undeformed. Okay, so because we reference the undeformed LO, right, the original length or the reference length, right, then that's why this is often called a Lagrangian strain. Right? So this is the one you typically measure in the laboratory. But there's other strain measures, right? So I could basically, one we call the log strain, and what we do there is we normalize with respect to the instantaneous length. So we integrate from LO to LF, the change in length, the infinitesimal change in length, over the instantaneous length. So that is the length at every step of the deformation, right? So I deform it an infinitesimal dl, what's the length, right? The total length of the bar. And I deform it a little more, what's the total length of the bar, right? So it's the instantaneous length as we deform it. Or you might think of it like in an experiment like L of t, right? Like as time progresses, the length changes, and we're always normalizing that. Right? So if you solve this integral, the answer is the natural log of LF over LO, or the natural log of our stretch, lambda. Right. Remember I said what you normalize it by is arbitrary? Right? I'm going to prove it to you. Right? We got one definition up there. Let me before I do that, let me just write out. Again, we call this the logarithmic strain. Or sometimes it's called the natural strain because the solution is the natural log, right? The natural strain. Or sometimes, particularly in experimental literature, you might see this called the true strain. I don't like that because in computational literature, sometimes there's another strain measure called the true strain. So I prefer to call it the logarithmic or natural strain. But yeah, remember I said they're arbitrary. Well, let's look at that first equation again, right? The engineering strain is equal to lambda minus 1. Well, I can simply rearrange that equation by solving for lambda. And we see that lambda is the engineering strain plus 1. Well, I could plug lambda in to the other equation. And we get the natural log of the engineering strain plus 1. That's also the logarithmic strain. Right? So they're related to each other. And in fact, if you do see the logarithmic strain in a paper from an experiment, it's unlikely that they actually measured the instantaneous length throughout the experiment. You can do it, it's just hard. I mean, you can do it, nowadays it's less hard because you have optical measurements and stuff that are pretty accurate. But, even before, ubiquitous cameras, high resolution cameras and digital image correlation and all that, I mean, there's still ways to do it. There's always been ways to do it, but it's just difficult. It's much easier to just go, to the engineering strain. All you need to know is the final length and the original length, and you can compute it, right? So if you see the logarithmic strain published in a paper, experimental paper, it's unlikely that they actually measured it. It's more likely that they measured the engineering strain and then just converted it to the logarithmic strain. Okay. So again, there's more strain measures. I'll just produce one more. Again, I'm going to use the symbol true. I don't really love, I'll use TR for true. But this would be if you normalized the change in length by the final length. And so again, in terms of lambda, that's 1 over 1 minus lambda. And this is often called the Eulerian strain. Or again, sometimes in computational literature, you'll see this as the true strain. And because of that confusion, I just don't like those terms, right? So, I would prefer to call this the logarithmic strain and this the Eulerian strain. Okay. But again, you can see, because I can solve for lambda, I can plug in the engineering strain there, rearrange the equation, and I have an equation, right, for that. So, because of that, there's a family of, there's a way to write these more compactly. These are called Seth Hill strain. And in a Seth Hill strain, it's just a way to sort of combine all of these. So you have a parameter m, and then your equation is 1 over m lambda to the m minus 1. And then, if m is 1, if m equals 1, then you get the engineering strain. If m is minus 1, you get the Eulerian strain. And if m is 0, you get the log strain. And to evaluate it in m and 0, you have to take a limit, right? But it works out to that. So yeah, it's just a little review, and we'll see how these come into. So this is all in one dimension, just simple concepts from undergraduate, but we'll see how these come into play in a three-dimensional continuous setting in the next, probably not today, but in the next class. Here's an aside. How many of you do experiments?
I have one question.
Sure.
The previous equation, the last one was m equals 0.
Yeah, m equals 0.
Should we have like a log?
You have to, huh? If you put m equals 0 into this, But you can't, I mean, if we get 1 over 0, it doesn't, see, what you have to do is you have to take the limit of this equation as m goes to 0. And if you do that, you get the natural log. So I got more.